Previously, we looked at kinematics, which is the study of how things move, and now we're going to look at dynamics or forces, which is why they start moving in the first place. We discussed Newton's laws in class, but I'm going to just show some key examples here, just refresh your memory of forces here. So, a couple examples here, just to jog down memory lane here. Suppose I got a box here, some object sitting on some horizontal surface. Let's call it box M here for mass. Normally, if this box is just sitting here, what forces would be on it? Well, right now, if it's just sitting here, we're going to have a force of gravity and a force normal. If I did push this horizontally, we could have a force applied. And if there was friction here, we could also have force of friction pulling it back. This is the general shape and diagrams that you're familiar with. Force applied, force normal, force gravity, force of friction. Well, what I'm going to do here is do something a little different and start pushing things at angles. And so rather than doing this, I'm going to just box this thing off. I'm going to take it and same shape. Here's my object, but I'm going to take it and push it down at an angle here, some angle theta below the horizontal. So that should be theta there. So here's theta, here's the force, and there's the mass. What you're going to get here is you're going to be pushing, and I guess call it a force applied. You're going to be pushing with a force applied in the x direction and a force applied in the y direction. Also acting on this object is good old gravity and a force normal and a force of friction. Now, just to how these all relate to each other, just to key you in. Well, force of gravity is equal to mg. Force of friction is equal to mu Fn. And these two we can calculate just knowing the angle and whatever the force applied would happen to be. Just I want to caution you when doing examples like this. In general, when we have this example, often force of gravity is nicely equal to force normal. In this example, that's not the case. I just want to prove it to you here. If you look at it, force of friction here, okay, V equals mu Fn, all right, that's fine. But notice here that there's a force AY. The applied force is also pushing down. Same with gravity. In other words, these two forces are both pushing down. This is the only force pushing up. And if this object is not falling through the surface, I'm assuming it's just staying on a flat table or surface, it's not going to be accelerating. In other words, Fn has to be equal to force of gravity plus F applied in the y direction. These two actually add up to Fn. If this was moving at a constant velocity or not moving altogether, in other words, it's not accelerating, then we also know that this force Ax is equal to force of friction. You'd have to be given more information to figure out this. In other words, constant velocity, is it accelerating? Which way is it accelerating? Is it slowing down, speeding up? But once you know those pieces, take a look very carefully at your diagram and how the forces add up. It's very important you look at it. In other words, you could have another diagram where I'm pulling up on an object. Let's say pulling a box along on a rope, and here's my force. Well, there's going to be my force X, and here's going to be my force Y. And of course you got mg, and you got normal, and friction will oppose this motion. But even in this example, you notice that force of gravity is definitely not equal to force normal. And the reason being is because, well, now I got y in the up direction, so actually Fy plus force normal would equal force of gravity. So I have to be careful of those two things there. So when you're doing diagrams there of objects moving, pushing, pulling, be aware of the components and how they add up. If it's in what's called equilibrium, equilibrium occurs when the acceleration is 0. Okay. In other words, there's no net force. You could have what's called static equilibrium, which means it's not even moving. In other words, the velocity is 0 as well. But for this one here, make sure you're aware of how those two add up. We did plenty of those in class. The couple other examples I want to show you here is what are called inclined planes. An inclined plane, well, let's take a look at it for a moment. I'm going to draw a big inclined plane here. So if I have an object sitting here, here's an object M, okay, just sitting there. there's going to be forces acting on this thing in every direction. The weird thing is that because it's angled, okay, and it's some angle theta, that's what this thing's launched at. This is what's called the angle of inclination, okay. Well, we know here that gravity is going to act down, and so gravity always acts, straight down here. I'm going to call that force of gravity. The normal always acts perpendicular to the surface, so there's my normal. Notice they're not in the same direction anymore. Gravity's kind of off, pointing down, and this one's pointing off at an angle somewhere. We know here that if, let's suppose, and I'm just going to say that this thing's sliding down, in other words, it's moving in that direction, okay, it's moving in that direction. If it was moving in that direction, that means friction is going to be moving in this direction. And there is no force applied here. I'm not pushing on this thing. So what's pulling this thing down the ramp? Well, it's going to be gravity. Now, if it's at a constant velocity, we know that the component that's pulling it down the ramp has to be equal to the force of friction in order for it not to be accelerating. But regardless here, let's look at some of the math behind this. Okay. So what I'm going to do here is I'm going to divide up this into components. And instead of, maybe I should have wrote, Fg over here. I'm going to get rid of this here. There's my force of gravity. Now, if I divide this one up into components, this guy and this guy, what you end up getting here is I get a component here, which I guess I can call Fg perpendicular, and this I'm going to call Fg parallel. There's my symbols for perpendicular and parallel. So this vector here I'm going to call perpendicular, and this one parallel. The reason being is because this is parallel to the ramp, and this is perpendicular to it. Now, where's my angle and how does it relate to this? Well, I can confidently call this theta. Okay, these are actually the exact same angle there. Hope you can justify it by looking at some of the symmetry of this by complementary angles here, but very quickly you can justify that this angle has to be the same as this one. So when you look at this, it's very important to know here that, well, if this is sliding down here, I know that the force of gravity that's perpendicular, in other words, this component, has to be equal to force normal because it's not sliding into the ramp or jumping away from it. It's just going down in this direction. So you can consider this like my new, x and y planes now. Really, we've just shifted. And because it's not moving this way, I know that force gravity perpendicular is equal to force normal in this scenario. And this is what you're going to have to do. And also force parallel here is related somehow to force of friction depending on if it's accelerating or not. So what exactly are these? Well, I know that this is equal to mg. And so just like before, this is going to be equal to, let's see here, this is going to be equal to mg cosine of theta. This is going to be equal to mg sine of theta. This is very, very useful when solving force problems. So when you do force problems, make sure you're aware here that force, I'm going to just call it force perpendicular. I'm not going to get rid of the x and y terms here, but I'm going to call force perpendicular. This is equal to mg cosine theta, and force parallel is equal to mg sine theta. One last thing I'm going to show you here is just regarding pulleys. So there's some things on inclined planes, but if you have a pulley system, let's see here. Suppose I had like a surface like this going down, and there's a pulley sitting there. I'm going to make this a massless pulley for now. This has zero mass. Suppose there's this object sitting there. It's going around another object. So here, let's call this M, and this one big M. Okay, so there's a big M and there's a little m. Now, when looking at this, okay, I'm going to ignore friction. Let's just say it's a frictionless surface here. What's going to happen here is this one's going to pull down because of gravity. Now it's going to accelerate it. So what is the exact acceleration of this entire system here? Well, my force of gravity, okay, is going to be pulling down on this. So let's see here. Actually, that should be a capital Mg. Should be capital M, pardon me, capital Mg. And so my net force is actually equal to capital Mg. The reason being is because nothing else is acting on this. I'm assuming it's frictionless. If there was friction, we could add that and take it away. But right now I'm assuming that this is going to be my net force. Well, this also equals Ma. The problem is, which M do I choose for the net force is equal to Ma? This is my net force, but for it to be equal to Ma, What's it accelerating? Well, it's going to accelerate this mass and this mass are all going to accelerate at once. And because the whole thing's accelerating, I have to make that equal to m plus big M times a. So if they were ever asking me for what is the acceleration of this setup here, where mu is equal to 0 up top, I could end up getting here mg over m plus m. And you end up getting some scenario. This is not something you memorize. Please don't do that. Just in terms of how pulleys work, they're just shifting direction. It's just like I'm pulling this object. That's my net force, a certain amount, like that.